Awesome. Great. Well, hi, everyone. I'm Katie from Hackster. Thank you so much for joining us today. And welcome to Motor Madness with the ZUBoard with Avnet and AMD. So today we're going to be following along with Adam Taylor as he walks us step by step through building a motor control project using Avnet's ZUBoard. So I'm going to start out by sharing a little bit about our speaker today. Adam is a world-recognized expert in design and development of embedded systems and FPGAs for several end applications. He is a chartered engineer, senior member of IEEE, fellow of the Institute of Engineering and Technology, ARM Innovator, and Edge Impulse Ambassador. He is also the owner of the engineering and consultancy company Aduvo Engineering and Training, which develops embedded solutions for high reliability mission critical and space applications. So Adam's current projects include ESA Plato, Lunar Gateway, Generic Space Imager, UKSA TreeView, and several other clients across the world. He is also the author of numerous articles and papers on electronic design and FPGA design, including over 440 blogs on how to use AMD Zynq 7000 SoCs and Zynq UltraScale Plus MP SoCs. So we're super excited to have Adam with us today. He's going to start us off with an introduction and give you an overview of the tools used in today's build along. And then we're going to move on to the project build. So if you have the required hardware on hand and have set up your device with the recommended tools for this build along, you should have a finished project by the end of this event. So hopefully you had a chance to set up your workstation before you joined today. If you don't have the hardware or you didn't set up your workstation, you can still follow along. So thank you so much for joining us. We are super excited for you to be here. So you can still follow along, even if you don't have all the stuff. Join in with any questions you have along the way. While we're doing this build along, there will be lots of time to ask questions. Adam's going to be going through those questions. So if you do have questions during the build, just pop them into the Q&A. There's like a little box, I think, at the bottom of your screen where you can type them into the Q&A. So with that, I'm going to let Adam go ahead and get us started.
Excellent. Thank you very much. It's going to be great fun this afternoon, hopefully, or morning or evening. What we're going to do is we're going to take a look at how we can build a simple motor control project that's controlling a brushless DC motor. We're going to do this based around the ZUBoard. Hopefully you can all see that. We're gonna do that today with the ZUBoard. I have be careful, I'll lift it up very carefully because it's in there. We have the motor here and ready to go, and that's connected to a micro E-click board that's going to connect into this part of our ZUBoard. What I'm going to do, hopefully, is I'm going to share my screen now. And I have literally a few slides just to introduce some of the concepts and such like that we're going to do. And then we're going to walk through a Vivado design and a Petalinux design. So if you're not too familiar with Vivado and Petalinux, it's going to be quite interesting. I think particularly we've done a lot over the years of Vivado type work and creating applications in Vivado. Petalinux, I think, is going to be quite interesting because not only are we going to look at how we can do the motor control, we're also going to use there's a couple of sensors on this board, particularly temperature sensors. So actually the first application we're going to create today is going to show us how to work with iOctal and things to actually control and develop that and read those sensors. So it's going to be quite exciting. So as we start, I'm going to skip over the who am I side of things because we've just had a great introduction there from Katie. So the things we need today are, we need to have installed Vitus on our machine. Now, believe it or not, this webinar has been in development for quite a while. So literally any modern version of Vivado, so 2022.2 onwards, you should be okay. Because we're going to be developing using Petalinux for the software environment. We're going to need a virtual machine or access to a Linux machine. If you're not familiar with how to do a virtual machine, how to create a virtual machine for Petalinux, there's actually a project that we've just created that will walk you through step by step on how to do that. But don't worry, because actually in GitHub, and I will share the link in a minute, I've put all of the output products from Petalinux anyway. So the boot.bin, the boot.scr, and the image.ub, exactly as we've configured them, they're all available in a GitHub repo, because if you want to follow along, even if you are following along with Petalinux and you've got that Petalinux build on there, it'll take much longer than what we've perhaps got put aside for this development today to actually be able to run through and build those images. So we're going to give you the build. We're going to give you the build artifacts as we go as well, and we'll give you the, of course, we'll give you the Vivado XSA and everything that you need to do that. We also need, obviously, we need the ZUBoard, the 1CG, and we'll need a power supply. So I have I've not turned it on yet, but once it turns on in a little while, you will hear the power supply going, and then we need a motor, which in my case is going to be a 24-volt motor, and the micro free click. So our objectives today really are to show how to run through this and how to get a final application up and running on our board. So just to give you a quick introduction, and it's a very quick introduction because a few people asked a question at the beginning when they registered for this thing to understand a little bit about the board here that we're working with today. So the ZUBoard, as I like to call it, the ZUBoard, it contains, you'll see in the center here, it contains our FPGA. So this is an AMD, got it right then, an AMD MPSoC UltraScale, and it's from the cost optimized portfolio. So it's the 1CG device that's in there. And what that means is that it's got two A53 processor cores. It's got two R5 processor cores. Obviously, there's a lot of surrounding peripherals that can be used there for that as well. And there's also a programmable logic, and that's what we're going to put into our design today. We're going to put the interface in for the motor control in the programmable logic. Around the board, as you look around the board, we can see that there are several things that are useful to us. On that design, we've got the Ethernet connection, and we're going to use that today for our debugging and developing our software application when we get to that point in time. We've got the UART and the JTAG. We're not going to be using the JTAG today because we're going to be booting from the SD card, but we are going to be using the UART initially to do things like find out what the IP address of the board is, so as we can connect to it and communicate to it. We've got these high-speed connectors as well, which are very similar and are compatible with some syzygy modules. You'll notice as well across the board, we've got a temperature sensor on one corner of the board and a pressure sensor on the other corner of the board. Now, rather nicely, this pressure sensor also gives us a temperature output. And that's one of the first things we're going to do in our design. Once we've got Petalinux up and running, to prove that we've got everything up and running and we've got everything that we need to be. So we've got all of the drivers installed, we've correctly configured the device tree, and we've done all that. We're actually going to talk to those two sensors. Now, what's really nice about these sensors, and I can't remember which way around it is, but one of these sensors actually communicates over I2C, the other one communicates over SPI, and we're going to show you how to create the system and the software that will work with both of those interfaces from Petalinux. And then we've got the click expansion port here, and this is where we're going to connect into our motor control application today. So it's a really nice, really efficient board. It's relatively quite small, and I would say, to be honest, it's probably the best bang for buck sort of development board that there is out there at the moment around the MPSoC type families. I happen to have quite a few of them sat on my desk at home that we use for training and so on. So I want to think a little bit, as we're going to do today, we're going to be working with electrical motors, and really just to give you some idea of what they are. So basically, the motors, that we're using in our designs, they allow us to convert electrical energy into mechanical energy. So we can supply them with an electronic drive, and they will give us mechanical energy on as an output. And we can use that for a range of things, be it something like a milling machine or a precision CNC machine. Maybe it's robotics, driving a robotics joint or something like that. And one of the challenges of doing this, and we're going to look a little bit at electrical motors in a minute, the very basics of it. And it's interesting, is one of the subjects that I really enjoyed at university was playing with the electrical motors and the drives. And then in the intervening 25 years, I've not done too much with them really, apart from the simple sort of driving. But the basics of this conversion is that as we do this, we're going to generate a magnetic field. And one of the key elements of the motor control, the motor driving that we're going to be doing across these applications today is we're going to be controlling that magnetic field. So we're going to use that. We're going to manipulate and use that magnetic field to actually create that mechanical energy. And depending upon how we do that is going to depend upon how efficient our motor actually is. And particularly if we work with a simple DC motor, like if you were as a child, actually based in the UK, but I think they were kind of across the world. You know, we had Skate Electrics kits which had basic sort of DC motors, and you'd race the slot car races around there, or maybe a model train set. You know, they tend to use basic sort of DC motors. But as you move into more complicated systems, such as your industrial control systems, drive motors, and such like, we really need a lot more efficient and a lot more sensible control. So there's a few things that we talk about when we talk about motor control, and we say this is really what we want to be able to do in this application is what is motor control. And the first thing for it really is it allows us to stop and start the motor, and that's really key, because actually a simple DC motor, as we've talked about, will start relatively easy. A brushless DC motor like the one we've got, if we don't understand how to start that properly, if we don't understand where everything is, the currents that are likely to be drawn, the things that are, the currents that are drawn, the magnetic field that are created, we might not get it working as we want, and we might actually cause some damage to the drive electronics. So we need to be able to very carefully and very considerately stop and start this motor. Obviously, once we've started this motor or stopped it for whatever reason, but generally once we've started this motor, we generally want to achieve a given speed or a torque out of this motor for its application, be it driving a car down a road, controlling as part of a milling machine, you know, milling a piece of metal or something, or moving a robotic joint. That's going to need a controlled speed or a controlled torque. And as well as when we do that, you know, we might also need to reverse the motor, so change the rotation of the motor from one direction to the other. So if we're driving a car or moving a joint, you know, we can't only move it into one position, we need to be able to move it into every position. If we're doing like a complex CNC type machining application, you know, we want to be able to not only drive the motor down, but pull the motor out and change it and move it about. And the final stage element is something that I talked a little bit about with the stopping and starting of the motors. We want to make sure that should anything fail, should there be any circuit faults or overcurrents, that we protect these motors, because this motor here on the example that we're using today probably cost me maybe $40 or $50, but in the real world application, you know, the motors are actually quite expensive, and they can be quite considerable, and we want to protect them from damage as much as possible. So we're going to take a look at this. So this is what we mean when we say about sort of motor control and how we can do that, and how we can do this. So if we think about the basics of motoring, if we go back to 20 odd years, back to when I was at university learning about all this, you know, we know that rotation is achieved in a motor due to the attraction between two magnetic fields. So in the simplest example that we were talking about earlier on, the DC motor, you know, like the cut type we have in the slot car type things, that uses one magnetic field, and that's located in the rotor. We have a second magnetic field located on the stator, and I'll show this in a diagram exactly what the rotor and the stator are on the next page. And typically what we do is we make one of these magnets permanent and one of these an electromagnet, such that when we pass a voltage through it, we create the magnetic fields, we create the attraction, and then we get the motor spinning. Now, obviously, the output speed, the output torque that's coming on that depends upon the magnetic field, and I'll change that typo in the slide in a minute, and the phase relationship. So one of the key challenges of motor control is not only doing that starting and stopping and getting the motor starting, but once you've got that, being accurately able to drive an actual required torque or speed with the efficiency that you want. Now, one of the interesting things we all learn about this at university, is when you're spinning a motor, when we're working with magnetic fields, not only are we getting the magnetic fields and the voltage that's going down, but we're also getting what's called a back EMF as well, coming back from the motor. That becomes really critical in complex motor control applications. In fact, that back EMF is going to be perhaps one of the most critical elements of the motor control that we do as we move through this. So just to give you an idea of the types of motors that we might want to work with and control, and we're going to put out there's a couple of other projects that we've done over the years on Hackster talking about how to control simple brush DC motors. So we'll send you the links to those as well. But if we have a simple sort of brush DC motor, it's really simple. They're really low cost, which is why they're in toys and such like. Really simple to control. We just give it a pulse width modulated waveform to control its speed. But they're more complicated to manufacture. The brushes which actually connect into the motor are particularly bad in their life, so they will expire, and they give bad EMC. So if we're trying to be nice and work in nice environments, this is going to give us some bad EMC issues. Stepper motors are very nice. When we want to do that precise positioning, that simple control. Stepper motors are very good. Induction motors as well are also very good for doing high power, high speed type of things that we need to use, but they're very inefficient, and they require very large voltages to work with, and the actual motors themselves can be really large. So we tend to find ourselves, like everything in engineering, engineering really is the art of compromise between what the advantages are and the disadvantages are for a particular application. But what a lot of people actually are using now when they want motor control is what are called brushless DC motors or permanent motor magnets. They don't have any brushes, so they have low EMI. They're really high efficiency. The downside is that you require a complex drive system to drive them. However, with modern electronics, modern ICs, and particularly things like the FPGA, we can actually get in quite a lot of this complex drive system and get this working quite nicely. So if we think about a really simple example, our simple motor example that we have here, we can see we've got two permanent magnets there, and in the middle where we have the rotor, we have a group of coils, and then we apply a voltage across the coils, which are connected via brushes, and that rotates and allows us to create that attraction between the permanent magnets and the electromagnet in the middle, and that gives us the rotation that we want for our motor in the simplest factor. Obviously, because we've got brushes, like we were just saying on the previous slide, it's electrically very noisy. The brushes are live, so it's not the best solution. But when we create this and when we apply this current through the rotor, what we see then is we get these two magnetic fields. We get the stator and the rotor magnetic fields, and they're roughly at 90 degrees, and that's important. And if you can remember that, as we go on for the next few slides, that'll be quite good. So that 90 degrees really is what gives us the maximum efficiency in the motor. Means we're not losing a lot of heat, and we're also getting the maximum torque, and we get that spins quite nicely. If we want to reverse the direction of the motor, we can flip the flow of the current, and it will go in the opposite direction quite nicely. But if we want to use a brushless DC motor, and this is not the best, perhaps not the best diagram in the world, but it'll help with the concepts. We actually, in this case, what we do is we flip it around a bit, and we make the middle the permanent. We make the rotor the permanent magnet in this case, And then we have 3 coils on the stator. Each one of these is 120 degrees away from each other. And by doing this, what we can do is we can push through a current. We can drive currents from the U to the W, for example, as you can see on this slide, and we will get rotation in the motor. And by switching where we drive the currents across the U, the V, and the W, and by switching those waveforms and the currents, we can get the rotation that we want to keep the motor rotating around. And if we reverse the current flow, then we get the motor rotating in the different direction. So it's a nice, relatively simple way. Well, simple is probably a bad word for it, but it's a nice way of doing this. And we can do this, as we'll see today, by driving through PWM waveforms to create this movement. What's this called when we drive this through? Actually, this is called 6-step because there are 6 drive phases that we can apply to the rotor positions, to the X, U, and V, to the U, Y, and V even, to create that rotation. So these are the 6 different paths that we can apply current, shown in green, through the system. And the red arrow is the angle of rotation. So this is a really simple method for doing this, and this is the one that we're going to be looking at today, because this is how the click-free actually works. It also gives us some interesting challenges. Doing this. So to do this, to control this, even to do the 6-step or the next more complicated one, which I'm going to talk about in a minute, what we need to know is the rotor position of where it is, so as we can start driving this properly. So there's 2 ways we can do this. There is the simple way, which would be to add some Hall effect sensors to detect the rotation, and we can do that. Obviously, that brings in additional cost and such like. Or we can sense that back EMF, and we can do some mathematics on the back EMF to determine when the polarity changes, as it's doing zero crossing, to work out the rotation of the motor. And to do that, we use the undriven phase. So if you remember, there's 3 phases, and we drive 2 of the 3. Phases. A sensor approach, as we say, requires more components. The sensorless requires more computational complexity. The final way that we can do motor control, and that's perhaps one of those, not that we're going to show. I'm not going to demonstrate that today on the ZUBoard, but you might have seen more recently the new AMD KD240 in the motor control kit, and this comes with an example to do this, and it's all implemented in high-level synthesis, which we'll talk about at the back end of this. But this actually does field-orientated control, which uses the voltages that are applied to the currents that are applied to the motor, but it also uses space vector modulation to actually create that 90-degree optimum angle between the two magnetic fields, and to give you the most efficiency. So the 6-step's quite a simple way to do it. The most efficient way, of course, is to use field-orientated control. We're going to use this, like I say, for this example today. We're going to use the click-free, and that's going to give us this 6-step one. It's going to work with any motor any brushless DC motor that works between an 8 to 28 volt range. It can drive up to 2 amps, and it's going to be controlled over I2C, and it's going to give us all those protection things that we need for the moment. The overcurrent, the voltage surge, the undervoltage protection. So it's going to help us quite significantly with our motor control applications there. And you can see here that what we have on the click-free, and I will show you mine at the end of this. I'll point it down. But you can see we've got the input voltage from our benchtop power supply. And we have the 3-phase motor outputs, the 3 motor phase outputs connected to that. And then we can control this over I2C, or give it proportional waveforms such as a PWM waveform or something. So this is what we're going to get started with looking at today. So with that, we'll I'll not save that. Don't save. With that, we'll get started on actually creating and building the project. I'm going to give you the GitHub link as well. Let me just move the things down on my slide. We'll also make the so the GitHub link is here. We'll also make all the slides and everything available at the end of the session, so as everybody can see that also. So let's. I'm sharing my screen. Everybody should be able to see my virtual machine running. In fact, I'm just going to stop sharing my screen for a second and just focus it on the actual window itself, just so as we get the best resolution for it. So that should do that and give us that. So let's just check everyone can see that due to the wonders of thing. And if anybody has any issues with what they see on the screen, if the resolution is not quite right or anything's not quite there, just give us a shout and we'll try and correct it and get it better for everybody. So what we're going to do first is we're going to start out like all these projects. We're going to start in Vivado, and we're going to start Vivado. Now, I'm not going to build anything today, actually, or maybe I'll build the actual XSA just to give us some time. I don't think we'll get time to actually build the actual final Petalinux image because that takes a while. To run through. So once we've come in here, what we're going to do, the first things first, is we're going to create a project, and then we're going to walk through the new project creation GUI. So I'm going to store this in my, I have a special folder somewhere on here called HDL projects. It is on here somewhere. I saw it the other day. HDL projects. And I'm going to give it a name, call it ZU Motor Live. Oh, slightly wrong name in there. And then we're going to tell it that this is a RTL project, so this is expecting VHDL or Verilog. We don't have any VHDL or Verilog files to specify at the moment. Everything we're going to create in this project, we're going to use using AMD IP off the shelf. And so we're going to leave this button. We're going to leave this button ticked here, and then we're going to come to this one where this next dialog. And on this next dialog, we get the choice to select between a specific FPGA part or an actual FPGA board. So we're going to pick an FPGA board that's already been pre-installed with Vivado. If it's not pre-installed, we'll come to that in a second. So you should be able to go to Avnet here. And you'll notice that there's this little arrow here, which shows that all these boards actually aren't installed. So if you don't have it, we can install it in a minute. But if I scroll all the way down to the bottom, I will see I have a ZUBoard 1CG development board. I've got this installed because I can see the picture. If you don't have it installed, just click on the little arrow here, and it will download and install. But this is the board we're going to go with. So we're going to go with this ZUBoard for development, and we're going to click on Next. And it's just going to give us a simple summary of the project here for us to begin to work with and look at. As it comes through, it's going to take it. It's going to open a project for us. We're going to see this nice little summary here. We're going to see a nice little image over here of the dev board that we're using. We'll see the product name, the family name, the product part. And everything that we need. We'll see that we have no utilization because it's not been started yet, no power estimation or anything like that. So what we're going to do is we're going to implement a processing system. So we're going to put inside, if you remember back, I said that this contains a processing system, processor cores, and programmable logic. We're going to instantiate the processing system. We're going to add some features to the programmable logic, and then we're going to connect it up to the processing system. We're going to make some changes to the processing system configuration as we go on. But one of the nice things about this actually is that Vivado is going to do a lot of the heavy lifting for us, which is going to mean it saves us a lot of time and effort. And if we run through this, we're going to build this product in Vivado. We're going to then create a Petalinux implementation. We're going to then create a Vitis applications, and we're going to create 3 Vitis applications. The standard one will be a hello world. We're then going to look at the pressure sensors and temperature sensors, and then we're going to look at the application for the motor control. And if we get through that in time, then I've got a little secret project, a little bonus project I published yesterday, which I think is actually quite nice, and I've built that into this project as well. So I'll show you that. So to get started with this, we're going to click on this one here, which is create the block design. We're not going to change any names, any locations, or anything like that in this instance. We're just going to click on OK, and this is going to open up a block diagram and an empty block diagram that we can go away and we can edit. There's some nice things if you're new to Vivado and you've not worked with this before. I'll give you a little bit of an introduction. You know, if we click on this tab here, we can see all the design constraints, all the sources that we want to put in there, any constraints that we've got. We can click on the design. We'll see that getting more as we go through it. We'll see there being elements in there. We can click on signals so we can see any signals that are in the design. The most important one though is this tab called board, and this is because Vivado is what's called board aware of the ZUBoard. So when you downloaded and installed the ZUBoard, not only did it say, here's the device that I'm using, but it also said, and here's all the connectivity that I've got around my system. So if you remember back to the one of the slides I was showing, and we were talking about the pressure sensors and the click interfaces and such like, and the syzygy interfaces and everything. Vivado is aware of some of these, and that's going to allow us to accelerate our development as we go through this, creating the hardware side of things. So now we've got this. What we're going to do is we're going to click on this little button in the middle to add some IP, and the first thing we want to add is that processing system block, that block that gives us the overall instantiates the overall processing system that's user the Zinc MPSoC. So into this block, I'm going to type Zinc, and that's going to narrow down our search so that we can see a Zinc UltraScale plus MPSoC processing core, and we're going to double click on that. And this is going to add the MPSoC to our design. If I double click on this to reconfigure it, what we'll see is initially you will notice that nothing is configured. So as we've talked about, and as you're aware, if you've seen my blogs, you know, the processing system, it has the application processor unit. This is where the A53 sit, in this case, 2 of them. We've got the real-time processor unit. This is where the R5 sit, again, in this case, 2 of them. And then we've got all of the things that are needed to create the system to work. So we've got the DDR controller down here. So we've got the DDR controller down here, and this is what it can work with. So it can work with DDR3, DDR4, LP DDR3, and LP DDR4. But there's nothing in it configured at the moment. And similarly, the I/O, which allows us to work with things such as, if you remember back, we were talking about there, the Ethernet, the USB, and so on. None of that's actually connected and configured to neither. So we actually need to configure this design, configure this processing system for our board. And this is this can be quite a challenge, because if you've done this by hand, if you've designed your own custom board, and that's always good fun, what we need to do then is we need to go through and we need to configure each one of these elements by hand for our custom board to make sure that it's going to give us what we want, and it's going to do what we want. Obviously, we're working with a defined development board, so really nicely, as well as the board being aware of its interfaces, it's also aware of its configuration for the Zinc processing system with respect to its instantiation on the ZUBoard. So if we click this one here, the Run Block Automation, you'll notice we get this Apply Board preset, and that's going to apply the preset to the board. So if we click on OK there. So while this runs through, if anybody's got any questions, please pop them in there. I'd be really interested actually to know in the chat if anybody's got any experience working with Petalinux or creating embedded Linux solutions for it, or how easy they found these, and what they're working on and what they're doing. So what we've got here, we've got the Zinkel Scale Plus block. Now you'll notice it's changed ever so slightly from what we had previously. We've now got 2 AXI interfaces on there instead of just 1, and there are 2 clock connections on the back here. So if I double click on this block here again, so we can recustomize it, we can take a look and we can see now how this design's been customized for the ZUBoard. So we can see, for example, now we've got the GPIO initialized, we've got the QSPI initialized, we've got the Ethernet, we've got the gigabit Ethernet enabled, we've got the USB, the SD card, the SPI, the I2C, and the UART all enabled, which is really nice. So now we've got all this. If we click on the DDR element here, we'll see that it's configured for the DDR as well. So that gives us a nice configuration of everything to go. We can take a look at the clocks. All the clocks are nicely configured. The output clocks, if I expand them all, what's that one? Expand all. If we expand them all, we can see all the clocks nicely configured. Everything's all set up as we want to be able to allow us to start working with this, which is what we want to do. For the time being, I don't want to make any changes to that, although we are going to make some changes to it coming up, but we're going to do it relatively systematically, as they say. So once we've got this,
Adam,
yep.
We had a couple of questions come in. I wanted to quick go through them before we move on to the next one. Was if you have an example of the brushless motor that you are using in this?
Yes, so the one that we're using, it was in the PowerPoint presentation, but we're using a Linix, which is LI. In fact, let me put it in the chat. Let me put it in the chat. So
yeah, do you want to make sure the drop down is to everyone too? I think the GitHub link didn't go to everyone, so just when you send it in the chat, make sure.
Oh, sorry, I didn't realize that. Yeah. No.
That's okay.
That's me out of practice with this one. So this is a 45 ZWN 24-40. So there you go.
Great. Okay, awesome. And then there was a question about software tools, if they require any specific features, CGP, GPU, TPU, etc., before proceeding to installation.
No, they shouldn't. They shouldn't require any. They shouldn't. The software tool should just download and install. If you follow through my creation of a Petalinux virtual machine, that should have helped you get everything set up on there, but you shouldn't need any add-ons or any plugins. Somebody also, I see, noticed asking if you can follow along using an Ultra 96 board, and yes, you can. The only issue is I don't have an Ultra 6. I was going to show you if I got one behind me on my thing, so I could go. The only issue is this. Unfortunately, I don't have one. The only issue is you'd have to route out what we're about to do. You would have to do a little bit by hand to connect to the low speed connector on the Ultra 96, because it's not going to be but yeah, you could do that and try it that way. But it's certainly possible to follow along. It's just going to be a little bit more fiddly on the Ultra 96 than it is on this one.
Great. Awesome. There was one other one about plugins or API libraries. I think I shared that link for the tutorial. There was a link for Vitus to set that up, and there was also a link for Petalinux that I shared in the chat as well.
Yeah, that's literally everything that we have. You don't need any special plugins or APIs or libraries or anything. It should just pick up and go.
Great. Awesome. Thank you. I think that's all we have for questions. I just wanted to make sure we got those before we moved on.
No problem at all. Please keep the questions coming. It makes it more makes it more interactive. And I'm sure as we go through this, I'm bound to forget things that I mean to say. So just please keep throwing the questions out there.
Awesome.
So now we've got this in here. We've got the processing system in the middle of our block. We're going to add a few. We're going to add a few of the elements to this block, and we're going to do that so as we can control and work with it. So the few things that we're going to drag across, and this is really nice. It's really nice about the fact that it's board aware. Is the first one we're going to do is we're going to pull across this click I2C, and we're going to pull this across onto the block diagram, and you'll see it puts us in a I2C controller that's connected to that's going to be implemented in the programmable logic. So this is not one of the I2C controllers that's implemented by the processing system. It's a logic I2C controller. We're going to also pull across. I'm going to do this. This might look a little bit out of order, but I'm going to do this in line with what I've got written in my instructions. We're going to pull across the PLGPIO push button. And that's going to give us a GPIO. So it's going to give us a general purpose IO registers. And they're going to be connected to, there's two buttons up the top here. It's connected to one of these that's connected to the programmable logic. The other one's connected to the process software. We're going to pull across the RGB as well, and you'll see it's going to sort of highlight where it can go. So we're going to pull that across. So when we pulled across the first RGB, it said, "Oh, the GPIO's got two banks. I can share that. I can use one of the banks of that." When we pulled across the second RGB, obviously there's not three banks, so it needs to create a separate one. So the idea behind this as well is I'm going to give you a Petalinux design, a Vivado design, and a Petalinux design that you can actually not just use for motor control on your ZU board, but you can use for experimenting and understanding how to do simple things such as GPIO, push buttons controlling LEDs, reading the pressure sensors, working with the motor control. So it gives you a nice base functionality, shall we say, for this development board. So now, having pulled those two across, we're going to pull across the temperature sensor, I2C, and we're going to pull across the syzygy DNA port, I2C. So this gives us a really nice set of connectivity that we want. Now you'll notice that each one of these has a AXI interface. So this is called a ARM extensible interface. And if we expand this one, you'll see that it's a memory mapped interface. So AXI has two distinct groups. It has a read channel and a write channel. And both can actually occur fully independently of each other. The write channel consists of write data, well, write address and control, write data, and write response. The read channel consists of read data, read address and control, and then the read data that comes back. These are implementing what's called the AXI Lite protocol, because this is not meant for doing bursts of data. It's just meant for simple register accesses because hey, I2C is pretty slow. So that's going to do that. It's the same for the GPIO as well here. And what we want to do is we need to connect these AXI interfaces up to this processor core here, and to one of its initiator AXI outputs. So we could do this by hand. We could put in our own AXI network and connect it up by hand, but it'd take a little while. So what we're going to do is we're going to run this connection automation. We're going to select all of them, and we're going to click OK. And we're going to let Vivado go through and do the connections. And then just to tidy up the diagram, we're going to hit this diagram, this button here, which will regenerate the layout. So it will give us a nice and simpler resultant block diagram. And what we can see now is the AXI, the master AXI from the processor. So this means that the processor is the one that's initiating the transaction, can talk via this AXI interconnect to all these peripherals that we've connected on the connect to all these peripherals that we've connected to our design. Now, AXI, as you might be aware or may not be aware, AXI is a point-to-point link, which is why you need an AXI interconnect in there to enable you to have one master talking to multiple slaves. Once we've done this, we need to make a few changes to the processor system. So what we're going to do is we're going to click on the processor system to reconfigure it. And then we're going to go to this tab here, the PSPL configuration. And we're going to first drop down the PSPL interfaces here, the master interfaces, and we're going to turn off this currently unused master interface because we don't need to use it for this application. And on the general tab here, we're going to come to the interrupts option, PL to PS interrupts, and we're going to enable these interrupts here. So 7 interrupts from the processor system to the programmable logic. And we're also going to go to the I/O configuration. Now, if you remember, I said one of those sensors, the pressure sensors, the temperature sensors, one of them is I²C, which is the temperature sensor. And the other one is SPI, which is the pressure sensor. And I didn't put there's no SPI connection on here. And actually so what we're going to do is we're going to connect from the processor SPI to the SPI, the pressure sensor SPI, that's connected to the programmable logic. So if you were to look at the FPGA device, the pins for the pressure sensor are connected to the programmable logic pins for the ZU1 device, and not the processor system's SPI, which is coming out of its MIO banks. So what we're going to do is we're going to go to the low speed tab here. We're going to go to the I/O peripherals here, SPI here. And you'll notice that the SPI1 is already allocated to these pins 38 to 43. We're going to turn on, SPI0, we're going to turn on SPI1, and we're going to select this option down here, which is EMIO. So what that means, it's called extended multiplex input and output. What that means is it's going to make the SPI pins from the processor core available to the programmable logic, and such we can route them through the programmable logic to I/O pins on the programmable logic and connect to that pressure sensor and start working with it. So we're gonna do that, and we're gonna click on OK. Give it a second while these things update a little bit. And you're going to see now we've got an interrupt input here, and we've got an SPI output here. Linux, because if we were using bare metal software, we wouldn't need to use interrupt driven, because this is a fairly straightforward, fairly simple system. We wouldn't need to use necessarily a process driven system. We could use a polling system and just an internal timer and just cycle round all these peripherals and do what we want to do with them. But Linux doesn't work like that. Linux needs a interrupt based system to work with these peripherals in the kernel. So we'll notice that the I²C, they all have interrupt pins allocated. The GPIO pin doesn't. So that's a great question that somebody's just popped in. So how do we know the addresses are for the EMIO ports and not just the pins? So it will actually just move the address that you use to talk to that SPI is still the same addresses as per the technical reference manual, but it's just the actual physical routing of the pins via the MIO. It comes into the multiplexed I/O, and then they come out of the multiplexed I/O into the programmable logic, and then you can connect to them, which is what we're going to do in a minute. So if we click on this, we can enable the interrupts for the GPIO, so as we can have interrupts on the GPIO. Does that answer your question, Robert, or was it a little bit more in depth than that? So we can connect that. We've got the interrupts occurring on all of them. What we want to do now is connect them to this to the processor. So we're going to add another block on there and call this concat. And we're going to put a concatenation block on. And this block, I'm going to pull down here a little bit. We're going to connect this block from here to here. It's output from there. We're going to double click on this. And we've got 1, 2, 3, 4, 5 blocks that we want to connect the interrupts from. I'm glad it answered your questions, and I'm sorry you've got a. I'm sorry you have a broken wrist. So what we're going to do is we're going to connect these the interrupt pins to this concat block. And we'll see those all going through to that concatenation block. Once we've done that, I think if we hit rejiggle this, maybe I'll tidy it up a little bit more. The next thing we need to do, the final thing we need to do actually, is to create the is to map out the EMIO pins. So if you remember, I made the SPI external, so not going out over the multiplex IO pins on the dedicated processor pins, but coming out into the programmable logic. So when I expand on this, what I see are several pins here. So we get the to support any functionality. So we get the input, the output, the tri-state pins and such like that we might want to use these. So what we're going to do is we're going to make these pins, some of these pins, we're going to use some of these pins and we're going to ignore some of these pins. So we're going to make the clock out because we're going to be the master AX on the SPI transition. We're going to make this one the master. So we're going to highlight the pin itself, just the pin, and we're going to click make external. And that's going to create as an external pin. We're going to do the same for this one here, the master 0. We're going to do this one, and we're going to do make external. Nope, I got that wrong, and I did the entire port. So we're going to do this pin here. Oh, no, this pin. Make external. We're going to do the slave select one, which is this pin here, and we're going to make that external. This is the most tricky bit of it all. If I get this wrong, it's not going to work. And then we're going to do the input here. So the input, so the master out, the master in, slave out. We're going to make this one here. We're going to make this external also. And just because I'm always a little paranoid with SPI and doing this, we're going to put a constant block. This will be set to a constant of 1, so it'll always put out a logic high because the slave select is normally done by the signal going active low. We're going to take this and we're going to connect this to the slave select input, just to prevent the SPI processor core, if there's any noise or anything from happening, thinking it's being addressed as a slave and causing any issue. So we're going to rejiggle that. We're going to redo the layout. And that then should look like most of the, I'm just going to check this diagram against my my expected diagram. And that then should look pretty spot on to what we've got. Hopefully, if you're following along, hopefully that makes sense to everybody. And if there's any questions or anything that need to be done, give me a shout and let me know. What we're going to do then is we can check the address editor, and we'll see all of the IP modules in the programmable logic that we've added are sat within the address space. We're going to go back here. I'm going to hit validate to just check that I've done nothing silly in my design. That's what we want to see. No worries, no errors, no critical warnings. And then we're going to go to the sources tab here, and we're going to click on the block diagram. And we need to ask it to make us a HDL wrapper. Now, whether it creates you a VHDL wrapper or a Verilog wrapper is going to depend upon how you've set your project up. I think by default it creates Verilog. Otherwise, it creates VHDL if you've told it. So I'm going to click create wrapper. I'm also going to let Vivado manage this wrapper while it's being created. Is there any questions so far on where we've got to? Please, if there is, just throw them in the chat, or any comments, pop it out there. So what you'll see then is we've got a wrapper. In this case, it's in Verilog, and we are then pretty much good to go. The only thing we need to do then is we need to add a constraint file, because the board's really this is really a nice thing about it being board aware. It knows what the pins are on the programmable logic for the RGB, the I2C, the temperature sensor, the scissor J, and the push buttons, because that's all contained in the board definition file. What it doesn't know is where we want to connect the EMIO pins, or if we want to do anything else. So someone's just asked a question: why are there 3 signals on Zinc per SPI signal? And that's a really good question. And the reason is because that SPI controller is able to act as a master or a slave. So that's where you get the I and the O. So whether the signal is an output or an input. The T actually is to enable you to drive a tri-state. Is to drive the tri-state for the I or the O pin if you want to. So it gives it a nice lot of flexibility for that interfacing. And if you want to hide them, we can just mask them like that, so as we can just see the signals that we're interested in. So now we're going to do this. We need to create a constraints file, and a constraints file is what tells us what pins to use or what clock frequency to use. Again, we don't need to worry too much about the clock frequency, because it knows this, because the clock is coming from the processor system and it knows what the clock frequency is, but it doesn't know what the constraints are. So I'm actually going to cheat a little bit here. If you go to the Hackster project where this is all defined, this is all written and put in there. But to save copy and pasting and doing this, I'm going to go to the project that I ran through and tested this with yesterday. And I'm just going to add in the constraints file from there, just to save us a little bit of time. So as we'll see a constraints file, and what we'll see in the constraints file is we'll see the I/O standard for the EMIO signal. So we're on a 1.8 volt bus. We'll see the pin allocations for those, so the F5, F6, and everything. And we'll also see that I've actually asked it to put pull-ups on the Zincs on the I2C pins, just to make sure that those pins have got a pull-up. Once we're ready to do that, we can actually implement our design, and I'm gonna run this now. This is the one bit I'm gonna build. There's another little bit coming up when we have to download Petalinux, but I'm actually, if you don't mind, I'll show you the command that we want to do it. But then I'm actually going to use an example that I built yesterday, because it has to go to Git and download an awful lot of stuff. And when my machine's on, when it's screen sharing and doing webinars and such like that, might take a little time. But it's going to build, and it's going to pull down, and it's going to pull through the runs. This shouldn't take too long, and then hopefully we can see the outputs of it. It didn't take very long yesterday when I built it anyway. And it is a AMD. It's being built on a Linux machine across the opposite side of the office that's got a Ryzen Threadripper in it and 128 gigabytes of DDR. So hopefully it should be relatively quick. And there's not a huge amount. There's not a huge amount in it anyway. So that's a good question. So when you say no LED pins in the constraints file, and that's a good point to talk about. So no, because the board definition file that you pull down for Vivado when you install the ZUBoard CG, it actually contains the pins for those LEDs and for the I2Cs. So everything is defined in the constraints file. There is at the end of this, I wrote a blog on it recently, how to create those files. So at the end of it, I'll put a link to that blog so you can go take a look at actually what's included in an example file. If you go to my website, I'll type it here while it's building. Let me just put it in the thing, which is www.adiuvo engineering.com. And if you go to the blog section on there, in fact, actually, let me see if I can find a link to it since it's still building. And it wasn't that long ago I actually wrote this blog. When was it? Is it this one? No. Board definitions. This is the one. Give me 1 second because I can't actually see my address bar. Control C. Control V. So if you go there, that'll show you how these files are actually defined and created. It's based around a simple board that we've just designed, but you can see that. So somebody else asked why we use the 1.8 volt constraints, not 3.3, and that's a good example. So this motor is, oh, look at that, bitstream completed, so it didn't take too long. So this motor, if I hold it up, this motor needs 24 volts. And the I2C, well, I'll show you what pins are in a minute. And it's controlled by an I2C. The actual chip on there is doing all of that translation. The reason why it's 1.8 volts is that's how the board has been designed, such that I/O bank is 1.8 volts. That's connected to the pressure sensor. If we were to go to reports, not a synthesis report. If we go to a I/O report here, you will see that you can see the banks that these are on, and you'll see the click. Let's find the click one in there. Somebody shout out if they see it. You can see these ones are allocated to 1.8. So I/O are split on a MPSoC device. The banks are split between what are called high performance and high definition. High performance 1.8 volt is the maximum that it can be, and it supports a lot more standards. Yeah, it supports. Thank you, Robert. It supports a lot more standards, high speed standards at 1.8 volt, and you get a lot more features than you do if you go to the high definition. The high definition supports 3.3 volts, and you can see the click SPI is actually on a high density one. Sorry, high density, not high definition, and that supports up to 3.3. But in this case, it's still running at the 1.8. Once we've got this, what we're going to do is we're going to come here and we're going to export our hardware design, and we're going to take out what's called the XSA from this. So we're going to come in here, we're going to click on next, we're going to tell it to include the bit stream. We're going to let it export where it wants into the project, and then we're going to click on finish. And then if we open up a file browser, maybe file system, ZUBoard, HDL projects, ZU Motor Live, you'll see this is the XSA that we've just exported from the design, and that contains the bit file. It's just a compressed file, so that contains the bit file, some hardware handoff information, configuration information on the system that's going to be used to help us develop this. Now is where it gets to be fun, because we're going to start working with Petalinux. So we're going to open another terminal window. And the first thing we're going to do if we've got Petalinux installed is we're going to source the Petalinux environment. So I happen to know that this is under source Petalinux 2022.2 settings.sh. Now, if you're not familiar with Petalinux, I don't know who's used Petalinux or not before, but it's entirely GUI-based. It's GUI-based. It's entirely command line based with some optimization. So we'll see this as it comes in. What I'm going to do then is I'm going to CD in. I've got a projects area that I have. We have a Petalinux project area that we have, and then we're going to come down here and we're going to create a Petalinux project, and we're going to do this using the command. And here's where I can never remember how to type. So we're going to create in Petalinux. And the great thing about Petalinux is there's only 6 commands, literally only 6 commands. There's a million ways to use them, but there's only 6 commands, so it makes it really nice and simple. But in this case, we're going to create. I'm going to make this a little bit larger. Yep. Well, let's create. We're going to give it a type, and we're going to tell it that it's a project. And then we're going to give it a name, and I'm going to call this ZU board live. We'll call it ZU board live. And then I'm going to give it a template. So we have to tell it whether to create this project and whether to give it a template for a Zinc MPSoC, for a Microblaze, or these days for Versal. So we're going to call it Zinc MP. And we're going to hit enter. And we're going to realize that I can't type because I missed a U. Petalinux. And that's going to give us a new project. And then we're going to CD into that new project that we've just created. And now what we're going to need to do is we need to tell it to pull through and customize for the hardware design that we've just created in Vivado. So what we're saying is take the XSA from Vivado and customize your Petalinux project to match this. So what we're going to do is we're going to use the Petalinux command. We're going to do config -- get hardware description. And then we're going to tell it where that XSA is. And we don't actually give it the XSA, we just give it the directory of the XSA. So make sure there's only one XSA in that directory. We're going to ADIUVO HDL projects, doesn't want to autocomplete, ZU motor live. Petalinux config, get HD and hit enter. And it's going to go away, it's going to pick up that XSA for us. And then it's going to generate a new project settings for us, I hope. And that's going to come through, and that's going to give us this configuration dialog here that we can use, and we can use to configure our system. So through this, we can change things such as whether we want the FPGA manager involved, whether we want to be a RAM disk or a XT4 persistent memory or something like that. For the time being, we're not going to change anything in this, and we're just going to click on exit and then save the details. I'm just a little conscious of time, so I'm not going to go through exploring that hugely too much. But then the next thing we want to do is we want to explore the kernel. So we want to configure the kernel because we need to add in some drivers for the kernel. So we're going to do Petalinux config. I'm going to do -C, and we're going to do kernel. Petalinux config -C, that's kernel. And this is going to take a couple of seconds because it's going to go away and pull everything down to actually create the kernel. So now is a good time to ask any questions you've got, because it might take a minute or two for this to be to pull down. So somebody's asking if you make analysis, is there any documentation describing all kernel root FS configurations? And that's a really great question. There's not a huge, I'll be honest with you, there's not like a huge compendium of configurations out there. There's some good places to start within the AMD ecostructure. So the user guide 1144 is really good for that. But obviously, what we're doing now is we're moving from being sort of embedded FPGA developers to moving over into being embedded Linux developers. And when we're moving that over into being embedded Linux developers, there's a whole world, basically the embedded Linux world is there for us to sort of pick up and to sort of work with and to make optimizations. As you'll see in a minute when we start doing this optimization, there are actually quite a few optimizations, configuration settings that we can make for the kernel. We're going to make some changes to the root file system. And we can run through that. So Robert, you were just asking about configure where the GitHub link for the constraints are. The constraints are actually defined in the Hackster project. They're there as text in the Hackster project. So that's the best place to take them from. What I will do after this project, after we've done this, is I will go and upload the actual constraints file and the software files that we're going to create into the application. I'm hoping this is going to run through quite quickly. If it doesn't, we'll give it a second or two. If it doesn't look like it's gonna finish in the next minute or two, we'll cancel this and we'll open one that I built yesterday, which doesn't have to do all this downloading, so as we can show what's going off. But we'll give it a minute or two, because at the moment it's going out to the internet to pull down all of the kernel files and everything to actually build. So it's going to Git to pull that down. I like to do things live, but maybe we'll have to just maybe we'll give it a minute or two and maybe we'll change. Does anybody else have any questions that we're going through on this so far? There is another project I actually created yesterday as a little bit of a bonus on there. So if you go to my Hackster project as well, if you go to Hackster.io, you'll see it actually. It's on the front page of Hackster. But this is quite a nice project because it shows you how. I'll pop it in the chat here. Shows you how you can use integrated logic analyzers that have been put in the programmable logic. If you're using an embedded Linux type solution, what happens is sometimes when you try and access it over JTAG, the Petalinux kind of locks it down and it stops working if you're using Petalinux to access the JTAG, the ILAs in the JTAG. So the project I've just shown you shows you how you can do that, actually connect to the ILAs using Ethernet and connect to it. And it's all built on the project that we're building today as a little bit of a basic. So somebody's asking, so the XSA is actually a zip file? Yeah, it's just a compressed archive file of what's included, what's needed for the software to be able to recreate a system that comes up and runs quite nicely. So it contains, like I said, the bit file, some C files, some XML files that define all that configuration. And I see actually a great question there from somebody asking about Petalinux having U-boot included, or does it do that? And actually, it does have U-boot included. So how Petalinux works is we have a first stage bootloader that gets loaded into the on-chip memory of the Zinc, but that bootloader is too small to be able to load something like a Linux kernel, and it can't execute from DDR for security reasons. So the first stage bootloader comes in, it configures the processor on here. It then loads in U-boot, so it then takes the time. It loads U-boot into the DDR memory, which acts as a second stage bootloader, and then it starts U-boot running. And once U-boot started running, U-boot then loads the image kernel into the DDR, gets that all up and running, and then hands it over to initialize the root file system and everything like that, and boot up the kernel. So it's a really good way of doing this. This is actually taking a little longer than I was hoping, so I'm just gonna hit Control-C. And I'm gonna change this to, just gonna exit that project for a minute, and we'll go to the one that I previously built, that I built yesterday, just so as we've got the time on it. And it must actually, I say yesterday, it must have been yesterday. Which one we're in ZUBoard. So we'll do CD ZU board motor. And then we should be able to do the command again, Petalinux config kernel.
Adam,
Hopefully,
there was a
yep.
question from Tom a little bit further up in the chat about the USB
yes.
microport.
Yeah, so it looks like the USB microports, the UART comms. How do we set that up? So that's initialized as part of the when we initialize that processor. That was initialized as part of that when we applied the automation to it, the block automation, and it configured it. That all set up. So all you've got to do is plug in a serial port, as you'll see in a minute when we move across to doing that. When we move across to doing that part, so it's kind of what's the word for it? It's kind of seamless for you to do that. Sorry about that, Tom. I missed that question. It was a very good question. So this is the longest bit of everything that we have to wait on when you wait for it to optimize this kernel. And the reason we need to do that is we need to include some device drivers that are present. So what we need to do is we need to scroll down here to the bit that says device drivers. And then down here, we need to go down to SPI support. And then this is already turned on in my example, because it's the one I worked through the other day. We'll see the Xilinx support's turned on by default, but what we need to enable is we need to make sure that this user mode SPI driver support is enabled. And that's what enables us to work with the SPI easily from the processor system in Linux, from the user space in Linux. So that's the only change we need to make to the kernel. Obviously, when you're doing this and you've got a little bit more time than what we've got now, feel free to take a look around, because there is actually quite a lot of things that we can look and explore with. And then we're going to exit that. And then the final thing we need to do is we're going to run through configuring the root file system. So yeah, actually, that's a good point for Tom. Actually, you do need to set the serial terminal up on your PC. It's gonna run at 115.2, as you'll see once we start this. So the slowest part of the entire project and this entire build is this little bit here, where you have to wait for Linux to do things. But I'm not going to go. I like to show things as they actually are, and not just sort of cut and paste, or so sort of so screenshots or anything. So give it a second or two, and it'll sort itself out. It'll come back to our command line, and then what we want to do is we want to change this here, the configuration element, to root FS. So we want to configure the root file system. Much quicker to configure the root file system. And under here, we see all of the elements that we can include in our root file system. The ones that we're going to use are under the file system packages and under base. And we actually want to enable the I2C. We want to enable the I2C tools option, so as we can see the I2C and work with the I2C tools. If we exit that and save that, once we've made that change, the only final thing we need to do is under the actual project itself, so the Petalinux project itself, when it's created and if you go to my website, there's a 2-hour tutorial on Petalinux itself, which will explain a little bit more detail. We can come to here, we'll see there's various elements of the project. We want to go to the project specification area and to the meta user area. So this is the meta user area is the only area we can change things, because everything else is automatically generated and is likely to be overwritten when it's being run through. So what we need to do is we need to go to the recipes BSP area, to the device tree area, and to the files, and to the system user.dtsi. And we need to make sure that our system user DTSI looks like this. And what this is doing is this is saying that the AXI, so by default, when the processor boots and it loads the kernel image, it doesn't know what's connected to the programmable logic. So we use a device tree to tell the processor what's connected to what it's connected to, so as it knows what drivers to go away and load. So what this is doing, it's saying for the AXI that it's telling it the clock frequency and that they're actually enabled and that we want to use them. For the SPI interfaces, it's telling it we want to use a driver called SPI dev to do this. You used to just be able to write where it says compatible SPI dev, but then there were some changes to the Linux kernel. Well, actually, I think they're a bit more strict on what AMD had to do with it. So if you list this device here, this is one of the devices that's under SPI dev that will work. So this is going to give us the ability to do SPI, to use SPI dev. This final bit down here is actually for the second project I just shared with you. And again, that's just telling it what driver to load in. Once we've made those changes to the device tree, we can come back to Petalinux and we can build the image by doing Petalinux build. And that'll take maybe 20 or 30 minutes to go through and build the image. It'll download all the code, it'll compile it all. And the outputs that you get from this will be presented in your project under the images directory. So you'll see under the images directory that you will get a boot.scr, which is a file that tells us where to go through and what boot media we're using to boot the device from. The image.ub, which is the image, and because this has got a root file system in it, this has got a RAM file system. This is included in the image.ub, and also a boot.bin. Now we have to create. There's another stage in the project where you have to create the boot.bin by using what's called the Petalinux package command. And that Petalinux package command will just tell it where the FSB, the first stage bootloader, the U-boot is, the PM firmware, and the FPGA bit, and they're all located in this directory. So if I up arrow a little bit, the one I did yesterday, maybe it remembers it. You'll see the Petalinux boot command. So it's saying, I want you to create me package this. I want you to create me a bootable image. The first stage bootloader is called this. U-boot is called this. The firmware for the platform management unit is called this, and the FPGA is called this. And the fourth bit on the end just says if one exists already, overwrite it, and that will give you a boot.bin. So what we then need to do is we then need to copy the boot.bin, the boot.scr, and the image.ub onto our SD card. And while our board's turned off like this, no lights on it yet, we need to put in the image. We need to put in the USB card. I'm going to plug in the Click 3 module. I'm going to plug in my power supply. Now I am connected as well to the USB UART, so as we can see that in a minute when it comes up. And I've also got an Ethernet. Can't quite lift it up, so I'll just tilt it down. I've also got an Ethernet cable connected to it as well, so that we can talk to it over Ethernet. Now, Giuseppe, someone's just asking if you update the block design, you update the system user by yourself. No, you can just run through. If you update the block design, export the XSA again, and just run through that get hardware description again, and it will automatically flip through and update the project for your new hardware design. So hopefully that makes sense. So now we've got the boot.bin, the boot images, and everything. And I'm gonna come over here. I'm going to turn on my board, and then I'm going to share my screen again, slightly differently in a second. I'm going to wonder why it's not actually working and why there's no serial port, because the USB cable's not connected. Let me just stop sharing my screen and then actually reshare my full screen, because we're going to move over onto my full screen now. So hopefully we can all see that. I'm going to minimize that one. We'll see this is giving gobbledygook out because I've not set the serial port to be 115.200. And we'll see that comes up with a login. Hopefully you can all see that. I know it's a little might be a little small, but we're going to switch over to Vitus in a minute anyway. A few things we need to do. We need to log in. So the username is Petalinux. It's going to ask you for a password. So I'm just going to set that to a simple password. Because this is a RAM-based file system, every time you reboot the board, it's going to ask you that. Is it going to ask you that question? But then we should see this up and running. And if I run ifconfig, I'll see my address on my network, which is 10.10.30.47. So now we can start creating some software and some applications to work on this. So I'm going to go to Vitus and open Vitus on my machine. I'm going to create a new workspace. So a workspace is just an area where all the files are located for this. I'm going to call this ZU Motor Live. And that's going to create a project. Now we need that to create a project in Vitus. We're going to need that XSA that we've just exported from Vivado. One of the nice things about using a virtual machine is you can copy and paste between the two of them. One of the nice things about having it on a build machine behind you, not only is it slightly faster, but we can also access it over a Samba network. So that's what we will do. So we're going to create a new project here. We're going to tell it that we want to create it from hardware, and then we're going to browse to it. And then we're going to go to my Samba share, and we're going to pick up the hardware file that we created yesterday. Give it a minute or two while it reads that specification. You see it's going to create all the boot processes, but we don't need that because the board's already booted. We're going to click on next. We're going to give it a name. We're going to give it a project name, so ZU board live. Hopefully you're all learning quite a lot as we go through this, and it's quite interesting to everybody. We're going to give it a name. We're going to call it ZU Live. ZU Live. The system name is going to come through because it just appends system onto the end of it. And what we're going to do is we're going to click this one here. So we're not like, if we're doing a bare metal application, we'd tell it to go for an A53 or an R5 or the PMU. We want this to run on Petalinux, on a Linux thing. So we're going to say that we're going to do a symmetric multiprocessing system with this. So we're going to click on next then. And you'll see that the operating system and everything's already filled in for embedded Linux. So we're going to click on next. And then we're going to go with Hello World. So we're going to click a simple Hello World program just to make sure it works. And I really hope it does work. It's going to take a few minutes to run through and build the project. And then once we've built the project, let me make this a little bit bigger. Actually, let me maximize my screen now for this. We'll see two elements to it. We'll see the platform and we'll see the application. So the platform will have got the first stage bootloader, the PMUF firmware. We're not going to use that, but it's needed. It's going to give us a hardware definition and an export for that platform. But because we're doing embedded Linux-based solutions, it's a bit simpler than that. Under the source file there, we're going to find a really simple Hello World project. And I'm a big fan of just trying something really simply initially, just to make sure that we've pipe cleaned the process and everything. So before we start throwing all of our code on there and making sure it all works or not, we're gonna we're going to do this. So we're going to click on this hammer to build it. It'll take a second or two. I'm going to move up. Didn't mean to do that. Although I hate TerraTerm that does that. I need to remember the IP address. So I'm going to put that on the screen down there. Somebody's got a question in the chat. Why use Cortex SMP as a processor? What is the difference if we use one of the first options? So that's a great question. So if we were to use one of the first two processors, we get the option of, and I'll create a project at the end. We get an option of whether we want to create like a bare metal application. If we wanted to run on a specific processor, say processor 0, we would create a bare metal application, or we would create a real-time processing application using FreeRTOS. And that would be compiled using a different compiler to what it would be if we were to compile that to run on the Linux, to run on a Linux environment. So using the SMP tells you that you're working in a Linux, that the operating system that you're using is Linux, and that actually you don't have a dedicated processor, because I don't know what processor this application is going to run on. I just know it's going to run on the APU, and the Linux real-time system is going to schedule and operate it to what's needed, if that makes sense. Once we've got this downloaded, once we've got this compiled, the next thing we're going to do is we're going to create a debug for it. So we're going to open a debug configuration. And over here in the debug configurations, we're going to create a TCF application. So we're going to click on New TCF application. Now, if we were doing a bare metal one, we'd be connected over JTAG. We could download the system over JTAG. We can't do that because obviously we're connecting to now a target that's running embedded Linux. So we need to connect to this using the Ethernet debugger and the TCF framework. So we're going to say we're going to do a Linux application debug, but then we need to tell it where is it that we want to connect to and what we want to talk to. So this is why I needed to know the IP address. So the IP address is 10.10.13.47. Oh, wrong box. We'll call that ZU motor. We're going to put the host name in there. We're going to tell it to test the connection. And really, luckily, because it's a live demo, so nothing ever always goes right, it's going to say that it's got an established connection. So it can now see. So my Vitus application is now talking to the board to do the debugging. So we're going to click on OK. We're then going to click on the application tab. And by default, it's going to tell us where it's going to download the application to, and where it's going to execute it from. Now, you don't always have these, or you have to be very careful with Petalinux, because this is the default application and you don't always know that it's going to be there, that directory is going to be there. So I'm going to do a really simple thing. I'm going to change this directory to make sure it works, and I'm going to put this in home Petalinux. And I'm going to do the same here. I'm just going to make this the working directory home Petalinux. Now, if I apply that just to save those changes and then debug, very quickly we'll see it runs onto our processor, downloads onto our MPSoC, pauses that execution so as we can start running it. And then if we click on run, we'll see hello will pop up in our terminal. If we go to the UART terminal here and we do ls, we'll now see that there's a ZUBoard live.elf in there. Nice and simple, hopefully, like I say. So the next application we want to take a look at it's a couple of things in the terminal window. So we need to check that we've got, before we can create an application, we need to check that we've got all the drivers bound correctly and that the device trees come through correctly. So what we're going to do is we're going to do ls dev. And that's going to give us a really long list of all the devices in our system that we can work with. But what we want to see is SPI dev 1 and 2. So these are the two SPI ports that we're talking to. And this is saying, yep, we've got drivers for these loaded. And as we go up to the top, we'll see we've got a number of I2C devices also available. So we can then use, if we want to, we can then use the I2C tools to sort of explore the I2C networks. If we do sudo, because we're not root, if we do I2C detect -L, yes, the console tab in Windows is the same as the console tab I'm working through now. So you'll see in this instance, you'll see our I2C network. So you'll see which one's mapped to which. And you have to be careful with this because it changes every time it builds, which one gets allocated to which one. So you'll see that I2C0 is the processor system I2C. And then 1, 2, and 3 are the elements, are the processing elements that we put in the programmable logic. So if we turn all this on now, and I turn on the motor drive, because the I2C chip on the motor drive click is powered externally, we can then do a few commands. We can take a look and see what the I2C networks look like. So we can do sudo I2C detect -y -r. Let's do 2 for a start. And we'll see 3F, which is, I believe, is the motor control chip that we want to talk to today. Now, this is useful because it means that we can actually see it and it's there. We can do this for the other ones. We can do this for 1. And we can do this for 0. And we can do this for 3. Now, one of these shouldn't have anything connected to it because it's going to the Syzygy high-speed expansion ports and there's nothing on it. So the third one, that looks correct. And it looks really nice and good.
Adam.
Yep.
There was a question about the TCF agent.
Yeah, I'm not sure about that, to be honest. I'll take an action though, and I'll send you I think we'll send a follow-up email. So I'll take a look at that, but off the top of my head, I'm not sure about the Ubuntu pre-built and what to do with that.
Thanks.
So now we've got this working, what we can do is we can have a little bit of fun, and we can create an application that's going to help us a little bit communicate with those I2C devices that we've got. So if we come down here and let me copy all this, so if I copy the C code from the Hackster project, come over into our Vitus project and copy and paste that in there, we can now leverage some of the interfaces from the that Linux provides us. So we can use, I said we can use the SPI dev to communicate with SPI, and we can use the I2C dev to communicate with I2C. So what we can do in our software application is we can open an SPI device using ioctl, and we can do the same for I2C. We can set the address that we want, and then we can come through and configure the SPI mode. So we can configure the SPI mode. We can start the I2C. We can configure the SPI ioctl transfer here. And then we can open the devices here. So we can open the device here to try and talk to the SPI. We can open it here to try and talk to the I2C. We can configure the SPI here. So we can set the read-write mode, the number of bits per mode, the speed that we're working at. And then we can send data to do it. So on SPI, on I2C, we can kind of send simplest data and get data and then read back. On the SPI, we need to send some stuff. We need to configure it up first and read it back. And then we can do the same here. So we just run through and set the software up and set the temperature sensors up, the I2C temperature sensors. And then we can build, if we build this application, what we'll do then is the two sensors have got temperature sensors on them. So they've got one up either side of the board. So if we look at this, my reference board, my safety board, just in case something went wrong, we've got temperature sensors either side here. And we can download our application and tell us what the temperature sensors actually are saying on our board. So if we run this and we can click resume here, we can see that we've got a little bit of a difference. Oh, I realize why that is. Stop. So as I said, this changes, so our I2C device doesn't have those temperature sensors on there, so that our I2C device is connected to channel number 2. So if we build this, download it again, we can click run. And we'll see now that we're getting temperature data across the board. One from very close to where the power supplies are located, and one at the other end of the board, so you can see the temperature difference across the board. And this is, and the reason why I included this is it's a nice example to show you how to work with the I2C and the SPI on the device. The next thing we need to do now, as we're getting towards the end of this session, I said I'd leave about 15 minutes or so for questions, is to actually look at controlling this motor. And because we're doing again over I2C, it becomes relatively simple to do. So let's take a look at it again. So we've got the I2C, we're opening the I2C device. I think that's wrong because that's the code that I wrote. So we're looking for an address of 52, and 52 is on channel 1 in this Petalinux build. I've then, in the previous design, I had a very flexible sort of, a very hardware engineered approach to software, a very hardware engineer's approach to software, shall we say, where I just wrote it all in one big long file and didn't have any functions or anything in there because I just wanted to prove that it worked. In this one, I've taken a little bit more time and effort and followed a little bit better software practices. So as we've created, there's no SPI driving in this one, but we've created an I2C read function, an I2C write function. We've then come through here and we've set up we open the device such that we can do reading and writing for I2C. And yes, Rick, the session will be recorded and made available, and we'll make all the build elements available. And everybody should have got my email address. So if you get any questions, you can email me, and we can do that. Somebody else asking about, can we update software applications in the field, not rebooting the board? And yes, you can update software applications in the field, just like I've done, where you've just connected to it over Ethernet. Once you've got Linux installed, you know, if you've got the appropriate security in there and systems, and I'm not going to talk about security and stuff because we don't have a huge amount of time left. But yeah, there's no reason why you can't update this in the field. You can even, because you're using Linux, you can change the programmable logic design in the field relatively easily. And actually, I was just writing a paper today. I swear this is truth, and I'm not just making this up. I was actually writing a paper today on AMD's new fallback software for updating the field. Their new AB approach that you see on the Korea. You can use that on any MPS OC as well. So that's quite interesting. So you can update remotely. So we're saying we don't actually need to communicate with the AXI directly. No, we're not. If we were to do a bare metal application, we'd be doing memory maps, you know. So we wouldn't communicate directly with the AXI, but we'd be talking to something in the memory still. So we'd be going for, say, like a specific hardware address, and we'd be saying, I want to read and write from this hardware address. I want to write these registers, read these registers to set it up and configure it. That's the beauty of Petalinux, is that it takes a little bit more to get set up, and there's a little bit more of a learning curve. But once you're up there, all those AXI type things that are put in there, the drivers, Xilinx, AMD provide the drivers. So in the user space, it's just, I want to use this, and you can access those by doing the function calls and the library calls, and it makes it a lot more efficient and user friendly to actually use. Why is it being done in the user space? It's being done in the user space simply because the user space is much simpler than doing things in the kernel. If I mess something up in the user space, I kill my application in the user space, and I can rerun it. If I mess something up in the kernel, I can potentially kill the kernel, and then we have to reboot, and we have to go away and go from scratch again. If you want to know about creating kernel modules and such like, check out the project the bonus project, shall we say, that I linked in the chat, because that shows you how you can create kernel modules and get them all up and running. It'll walk you through doing that if that's what you desire. But the reason I'm doing this in user space is it makes it nice and simple. Once we've got that, because we're working with this specific TI device on there, what we need to do is we need to write some configurations, some registers in there to configure it. So what we're saying here is we're writing to the I2C, we're writing to the I2C device that we've opened, the I2C address, which is 52, and then this is the register address that we want to write to, and then this is the data that we want to write to that. Want to write to that application. So let's build this. If we do this right in a minute, the motor is going to start spinning, and then you've got full control of the motor. So what we're going to do then is we're going to do some reads. So we're going to read the speed register, the status register, any fault registers, the system optimization registers, and we're just going to, once we've done that, we're just going to sit there forever and a day and run through in a loop. I'm going to put this down here on my desk. I'm going to tilt the camera down. I'm going to find a way. Maybe I'm going to take this under here a minute. Sorry about the camera. It looks on the camera. Yep. I've managed to break my feed. Is that going to come back or not? I don't know what's gone off there. Ah, yes. Yep. Sorry about that. I don't know what went off there, but that was a slide. So that's there. So if we do this and we download this, should have put a little bit of tape on the end of it, but you can see the motor trying to spin. We'll hit run. And there you can see the motor starts, and it starts spinning. Where's it gone? Quite nicely. I'm not going to. Here's how Adam lost a finger on a webinar. But we've got control of that motor now. We can manipulate it and change it within our software application as we want to do that. So let's just put the camera back for a second now. So any questions on that as we kind of get it all to the end and sort of get it working? So we've gone through and we've built a processor system and Zinc system using Vivado. We've then gone through and customized it using Petalinux to include the drivers that we want and putting the elements that we wanted into the root file system. And then we've booted it and checked it all through. We've written a couple of software applications, one which just a simple hello world, one which tests out the SPI and I2C just to show you how to work with it and get going with it. And then the final one just gets the motor up and going. Now, what I will do, and I'm not going to do this now, but now we've got this all working, my next plan for the next Hackster project is actually to put pink around this. Is actually put a pink wrapper around it, put some sliders on it so you can actually change the control of the speed in sort of real time using pink and its capabilities to give it a little bit better application there. So we have about 10 minutes. We have about 10 minutes left. Does anybody have any questions that they would like to see, or would you like very quickly to see the because I think this is the board that I put that in, the ILA working over Ethernet, so as you can see that working very quickly, the bonus project.
There was a question from Christian about two different applications on Vitis, just up in the chat a little bit. I want to make sure.
Oh yeah, I see that. Can you run and build different applications on RF codes in the batches? Yes, you can. You can build whatever applications you want on there. So if you come back to here, where's my mouse gone? So if I do debug configurations, so you'll notice here I did the single application debug because I'm debugging a single application. When you're doing bare metal, you can do the system project debug, and this will allow you to set up multiple system targets. So if you've got the R5 cores in the split, remember by default the R5 cores work in lockstep. So if you've got them in a split process in the performance process, you can put two cores on, you can put two applications on them, and use this system debugger to do it. You can also do that if you want to put applications on the APUs as well. So you can put applications on the APUs and it will download them all. It will get them all up and running. And if you've got any microblazers in there, then it'll get the microblazers running as well. So that's the way to do it. I'm just going to turn that motor off because it's making my desk vibrate quite a lot. And there you can see when it goes down with this demo, it now starts reporting errors and such like. So that's a great question. Is the motor controlled through the I? So the motors are actually only controlled via the I2C. So using the chip, you can kind of control everything you want to do with that using the I2C device, I believe. Or maybe I need to add a GPIO in to change the direction. I'll double it. He certainly doesn't use the speed. Certainly doesn't use the speed action. I'll double check on the direction pin. So somebody just asked, is it possible to do BLDC with field-oriented control with position without an external module direct from the FPGA? And the answer to that, of course, is yes, you can. The AMD KD240 is another board. And this comes with a complete BLDC FOC application. It's got all of the high-powered drivers you need. Obviously, whenever you're doing something with motors, you need some sort of, you can't drive it directly from the pins of the FPGA. You need some power stage, but that has the power stage included on it as well. And there is, if you go, we'll send this out in a link. But if you go to the Vitus libraries, I think the Vitus accelerated libraries, and go take a look under there, you'll see HLS modules that will do field-oriented control, SVM. You'll see the space vector modulation as well that's needed to do field-oriented control and get you the best one. But there's modules all under there to do that, and it's all free, so you can just go grab it and use it. The only reason that we didn't do the full field-oriented control with this example is we wanted to do the project based around the ZU board, and you have to then work with the interfaces that are available. Robert, you're asking about the higher current. In there, the higher current coming from the external microclick. Actually, there's a power supply. I don't know if anybody noticed, but there is a benchtop power supply on my desk that is providing the power to the so that's providing the 24 volts to the clickboard. Somebody was just asking if we can share any references on how to use the real-time processors in the MPSoC, and yes. We can. We partnered with AMD, not AMD. Sorry, we partnered with Avnet to do some training on how to use the ZU board for hardware, software, Petalinux. So and there's also training on there for the Mini Z and the Ultra 96. We'll include a link to those in the email that comes around, so as you can see that and go take it. And that'll teach you how to work with bare metal, with Linux, with everything. It'll take you about 3 days to work through the course, but it's well worth it. And the last one, in real application scenario, what would you choose? Control the motor, R5 or APU? So to be honest, I wouldn't use the R5 or the APU, and that's the reason why we have an FPGA here. So for the example, with the KD24 one, KD240 motor drives kit, all of that drive waveform is implemented in programmable logic. So all of the Clark transform is implemented in the programmable logic, and that's what gives you that determinism, that accuracy, that low level control. And then basically you can just have Linux running on the APU, controlling it over a industrial control interface into that to actually just control the speed, the torques, and everything. Oh, actually, that's not true. It sets the demands for the speed or the torque, and then the FOC control algorithm makes sure that that achieves the desired solution. Any other questions? Any other points? I'm glad. I hope it was helpful to everybody. And it's been great fun. It's been great fun for me to do. I was really nervous. I said to Katie when we started this, I said, we'll probably be done within about an hour. So I'm quite surprised it actually took the full 2 hours.
Thank you so much, Adam. As always, we love these. Hopefully we can do some more again in the future. And we definitely appreciate you all coming. So thanks again, Adam. And
no problem. It was my pleasure.
I hope everyone has a great rest of your day. If you do have questions, you can always send an email to our help desk as well, events@Hackster.io. And then I don't know if Adam shared his information, but we can make sure we get.
I think my email address is quite out there on the internet.
Yeah.
I think most
we
people,
can make sure you get connected.
Adam@aduboengineering.com, but I think most people know it.
Yep. All right. Thank you, everyone. Have a great rest of your morning, evening, afternoon, wherever you're at. See you next time.
Bye.